All right, so thanks for coming to my last minute talk and staying awake for a little while longer when I give the last talk of the conference. So I'll be talking about this paper that came out in May together with my co-authors, Stefan, who is here in the audience in the back, and Philip and Josh. I've given a short talk about this, I've given a poster about this, and I'm going to complete the package by now giving a long talk about it. So to give a little bit of background motivation, so we had this paper from 2 years ago by Chandrasekharan, Longo, Pennington, and Witten, which I will refer to as CLPW for the rest of the talk, in which they argued, well, we already know by now, after 4 weeks of lectures and talks, that if we take any quantum field theory, we consider a local subregion, we consider the algebra of local observables, that turns out to be a type 3 algebra according to the von Neumann classification of vectors. And we know that those have divergent entropies because they have no good density matrices, nor they have good defined traces. So what they did in the CLPW paper is, okay, let us look at the sitter space, and let us just concentrate on the static patch. And since that is a closed universe, like compact slices, no boundary, we have that the broken gauge group, so the gauge group along this world line of the observer, has to be acts as a constraint for our states and our algebra. But what they focused on is on the time translation part of this constraint. So the compact group of the rotations around that world line we're going to ignore for now. They turn out to be not really relevant for the story. So we will concentrate on the time translations which are generated by this modular Hamiltonian, the boost Hamiltonian of the sitter space. And so our constraint H is just that Hamiltonian. But so it turns out if you look at the algebra of gauge invariant operators, so you apply the constraint on the algebra, that algebra is just as nicely type 1, but it's just the identity component, it's just complex scalars. So it's very boring because we cannot really measure anything. So instead what they
really sorry, is this static patch?
Yeah, so these red arrows.
And then H equals HS, what exactly is it?
Well, I just call the constraint H, it has to be set to 0 on states. And the algebra, so constraint H is just HS.
Okay, but the total energy vanishing will involve both static patches, right?
Yeah, that is this HS.
Oh, HS is for both static.
Yeah, so it's forward time translation on the static patch and backwards in the because if you would split, yeah, the whole thing about type 3 is that you cannot split it up into Hamiltonians which are both finite. But this is if you just consider the algebra on the static patch, and you would like split it, then the left part would act trivially on it. But here it's a full boost Hamiltonian of the static patch. So instead, what the authors considered is, okay, let us physically model this observer along this world line. So we add this momentum. So we call it a clock in our paper. So they add this observer P. And their original paper was called Q, but for notation we just call it P. We go to the kinematical Hilbert spaces now of factorization between the system, which is just a sitter, and this observer Hilbert space. And our constraint is now HS plus this P. And then when you then look at the gauge invariant algebra with this constraint, it turns out to be much richer because it's not trivial, just the scalars. Namely, it consists of these two sets of observables, which we will talk about later. And this algebra turns out to be isomorphic to the cross product. And then it's a result from Takesaki that this cross-product algebra is a type 2 algebra, which means that we can have well-defined entropies and well-defined traces. And this is the main motivation of this paper, because we want to highlight, or I want to highlight, that this is just nothing but introducing a quantum reference frame and then taking the perspective of the observer to describe the system. So for the talk, I have the slides with takeaways. I will go over them in order. So I will begin with these two takeaways, that we implement the constraint on states, because there are two related works, but they only consider the constraint on the algebra and not on the states. And it's actually important that you also apply the constraint on the states. And then we will also extend to bounded clocks from the start, because this P just has the full line as a spectrum, but you can also imagine that you have a clock with some bounded spectrum, or like unions of finite intervals. So let us begin by talking about these clocks, or more generally, let us define what a quantum reference frame is. So whenever you have a theory with some gauge group which acts as a constraint, we know we want to look at states that are invariant on this constraint, an algebra which is invariant on this constraint as well. So what we do is we create a dynamical reference frame by taking a subset of the kinematical degrees of freedom, which are as gauge variant as possible under the same gauge group, such that they can nicely deparameterize the orbits, and then we can describe the system, the remaining degrees of freedom, relative to this reference frame, such that the description becomes gauge invariant. And when you say that they also have to be adhere to the quantum laws, then we call them quantum reference frames. Now, in the case here at hand, we're looking at the one-dimensional group of time translations. So instead of quantum reference frames, we will just call them quantum clocks. So let us generally look at this constraint here. So our constraint is of the form HS plus HC. So HS can be very general, can be a quantum mechanical system, can be a system of spins or just particles on a line. But in our talk, we will be mainly focused when HS is focused on the case when HS is somewhat Hamiltonian for some type 3 algebra. But it can be much more general as well. So then given this HS and HC, the goal is to construct a time observable T, which is conjugate to our clock Hamiltonian, such that we can then describe the system in the evolution of some internal time set by the clock. But there is a problem. So normally it has been proven by Pauli, Unruh, and Wald that if HC is a bounded clock, then T is not self-adjoint and nor monotonic. But this can be overcome by considering covariant POVMs instead. Yeah, the spectrum is bounded. Yeah, in one direction. At least one direction.
Oh, so just the fact that if it has a lower bound is
enough. Yeah. So how do we create this time observable? We start by creating these clock states from the energy eigenstates of the Hamiltonian. So this integral over the spectrum of the clock Hamiltonian. And for this case, we will just consider it to be a non-degenerate continuous Hamiltonian. You can also consider periodic or degenerate cases, but we will just focus on the simplest case. Now, some properties of these clock states is that they're covariant, so they just evolve with the clock Hamiltonian. They form a resolution of the identity on the clock Hilbert space. But more importantly is that if the spectrum is not a full Royal line, then the overlap between two clock states is not proportional to the delta function. So there is some what we call fuzziness between the clock states. You cannot perfectly distinguish between two times of the clock, of the quantum clock, when the spectrum is not a full line. And if it is, then we call them ideal clocks, because then they're perfectly distinguishable. So from these clock states, we can create this covariant POVM. I will not give the definition of it because it's not really important for the rest of the talk, but I will. You can go to our paper and look up and see what it actually is. But this POVM is then self-adjoint and monotonic, and this circumvents the issues I presented before, because this will be self-adjoint and monotonic for any spectrum sigma C bounded or not. But we're more interested in the first moment of this POVM, because this will be our desired time observable. Because as you can see here, we can create this n power moments, and then if we take n equal to 1, we have this commutation relation which is our desired time observable, which is then conjugate to our clock Hamiltonian. And then we will use this this time observable to then dress our operators in a gauge invariant manner. Yeah. Well, T itself will not be self-adjoint for a bounded spectrum, but the covariant POVM, which is actually just this without this T in front, and for like some Borel subset instead of the real line, that will be self-adjoint and monotonic. What do you mean it will break down? Because the clock states are defined. The clock states are defined for all values of T on the real line. I mean, yeah, so the covariant POVM version of this is without this T and over a finite range. But for the first moment operators, we do define them over the whole real line. Maybe that's something I shall look in then after this. So yeah, going back to these clock states, now if we've defined them, we want to use them to apply a constraint to our kinematical Hilbert space and to our kinematical algebra. So starting from the kinematical algebra with our constraints, we define this physical Hilbert space, which is basically just the Dirac quantization where we want our our field constraint acting on these physical states to vanish, which would mean that if you take any exponential of the constraints, which would generate external time evolutions, that would just act as the identity on any physical state, which is what we expect by saying that these transformations are gauge. However, since we're looking at the time translations, this group is non-compact, and this means that these physical states are improper and not normalizable. However, they're not normalizable in the kinematical sense. So how to overcome this is that, one, we can look at refined algebraic quantization, and it is that we define a physical inner product instead of a kinematical inner product. So we have this pi phys here, which is just an integral over the full gauge group. And this ensures us that this inner product here, so this inner product, so these two are physical states, these two are the representatives of the kinematical states, and that will be properly normalizable. So that's why we define, so we have to define a new physical inner product instead of just using the kinematical inner product. Now in CLPW, they took another approach. They defined the co-invariance, which is based on some cohomology of the ghost numbers. I will not explain this because it's not important for what comes, but if you want more information, you can go to that paper. But the co-invariant approach is also a valid approach to define physical states. Then for the algebra, if we just look at the total algebra, so we have the system algebra and then the bounded operators on our clock Hilbert space, and we construct then all the gauge invariant observables, they fall in two subsets. Namely, we have these relational observables in the sense that they measure the value of some system observable when the clock is in a particular state. And that can be read off from this expression. So we have our system observable and then this projector on the clock state tau. So that's what we mean by, okay, it's a value of A when the clock reads tau. And then we have this conjugation with the gauge group, transformations, and then we just integrate over the whole gauge group as like a coherent group averaging over the whole gauge group, and that makes this observable gauge invariant. The other observables are what we call clock reorientations because they're just unitary evolution by the clock Hamiltonian, and conjugating this observable here with this evolution just shifts this tau label, and that's how we get a relational observable for all times of the clock. And these together make up your gauge invariant algebra. And especially in the case if we're dealing with the ideal clock, then this form should be reminiscent from one of our earlier slides, namely this is exactly, if you set tau to 0, this is exactly the same form as what CLPW had for their algebra in the sitter case. And you can indeed prove that this algebra then, for ideal clocks, is isomorphic to the cross product algebra. So then we at least know that this algebra will be a type 2 algebra. Now, if the clock is not ideal, then we are rather dealing with a subalgebra. But the subalgebra can be formed from conjugation by a projection operator, which is itself an element of this algebra. So then we know that it will also be a type 2 algebra, just like in the ideal case. And just for completeness, because this whole construction is acts on the kinematical Hilbert space, you also need to define some physical representation to map these operators or push them to operators on the physical Hilbert space. And we will just call this R. So then this is the gauge invariant way of describing the system relative to some clock. And it's also called the perspective neutral way, which I will explain why later. But to then describe the system, you just have to evaluate these gauge invariant observables in the state psi, in our physical state, just for different tau. And that would mimic our evolution with respect to the clock. Now, there's also a second way, which is important for the equivalence, namely the Page-Wouters way, which is more akin to a gauge fixing. That is, instead of considering these relational observables, we condition physical states on a certain clock reading. So we take a physical state on the left, and then we define a new state, this psi of tau, by just acting with the bra of the clock state on that physical state. And this is more akin to what we would call a relational Schrödinger picture, because now you're looking at relational Schrödinger states, where psi is the state of the system when the clock reads tau. And the same can be done for the algebra. You take your gauge invariant algebra and you just conjugate with this R map, and then you get these operators here, which are just bare system elements. and then these U unitaries of the clock of the system Hamiltonian, which generate your time evolution for the system, for the relational Schrödinger states here. And they're conjugated by this projector which projects on the overlap between the spectrum of the system and minus the spectrum of the clock, such that there will always be combinations that will will lead to the full constraint being 0. And then it's an easy exercise to prove that this state evolves with the Schrödinger equation with the system Hamiltonian. And moreover, since this projection is a unitary, we see that we can see that evolution in the physical gauge invariant in the physical Hilbert space with these gauge invariant operators is the same as evaluating these bare elements with these relational Schrödinger states. So how you can describe evolution is just similar. You take these expectation values and now you let this star element here run by acting with this with the exponential of the system Hamiltonian to get your time evolution. So we will refer to this gauge fixing as page-routers or as PW. Now that we've given this small introduction to quantum reference frames and quantum clocks, we will come to the main slogan or the main part of this talk, that CLPW equals PW. And it doesn't mean that CL equals 1. It's just, yeah. So how do we see this? So let us recap the situation. So we have the sitter space. We have our constraint as HS plus some Hamiltonian here, and then and minus H2 on the causally disconnected patch. I did not talk about this minus H2 in the beginning, but this turns out to be important if you want our gauge invariant algebra to be a von Neumann vector. If you don't have the second clock, then the whole machinery actually doesn't work and you can't really look at the cross product algebra. So that's why we add the second clock. So then they create states by the co-invariant procedure. So they have this map T, which directly maps from the kinematical Hilbert space straight to a tensor vector of the system and the Hilbert space of clock 1. And you can conjugate the same algebra, so the algebra on the static patch dressed to clock 1, the algebra of the complementary patch dressed to clock 2. You can conjugate it with this T-map, and then for at least this algebra invariant, with this algebra, it maps it to this bare element with then some evolution operator HS plus H1. So then one might think, if you've paid attention to the previous slides, that is this the same as describing the static patch with clock 1 from the perspective of clock 2. And this turns out to be right. So what CLPW consider is that they consider the algebra of this patch dressed to clock 1, but from the perspective of someone who lives in the causally disconnected patch. And you can see this from this equation, namely, if cat psi is some kinematical state, and you act with this map that maps to this tensor Hilbert space, then it's the same as if we had first acted with this should be a phi. This should be a phi epsilon psi, but never mind. So it's the same as first acting with this physical projector that maps you to a physical state, and then you can page-router's condition on the time reading 0 of clock 2 to get this state, which is then the relational state with respect to the time of clock 2. And it's actually also, you can also see this as kind of an inverse way of, if you compare both maps, then this T-map first conditions on clock 2 and then integrates over the whole gauge group, while this map here, which we call the page-routers map, actually first integrates over the whole gauge group and then conditions on the clock 2. So it's kind of like, you could kind of see it as a commuting diagram where you first gauge invariantize or you first condition on the value of clock 2. So then we come to the main point of this paper, is that these observers with clocks introduced in that paper, these observers are exactly clock quantum reference frames in the sense of this whole quantum reference frame theory that has been constructed for the last decade. And since this is the main point of the slide of the talk, I will stop here for a minute to take any questions people might have in the audience. Okay, if there are none, I'll just continue with the other points. So now that we've explained why these clocks are just quantum reference frames, let us look at use the machinery from quantum reference frames to maybe perhaps generalize what CLPW did. So let us first consider the case where we have multiple clocks, so more than 2 clocks. So we consider a Hilbert space, which, so we consider any space-time. It could be the sitter, for example, instead of this picture. But we have an arbitrary number of clocks, and it's not important in which patch there exactly are. So our full kinematical Hilbert space is then just a tensor product, and our constraint is just the sum of the boost Hamiltonian and all the clock Hamiltonians. So we're really dealing with a quantum field theory system, but with quantum mechanical frames. So then the algebra we're interested in is then just a subset. We take a subset of all the clocks we're interested in, so we call it R, and then we single out a single clock, C subscript I, which will then be our clock with respect to which we will describe the rest of interest. So we can construct this gauge invariant algebra again, so with our relational observables with respect to clock Ci, and then the clock reorientations of that clock. We can map it to the physical Hilbert space and this representation, and we will know that this is a type 2 algebra as long as there's at least 1 clock in the complement. It's for the same reason why we had to add a second clock for the de Sitter case. And then the goal is, okay, we have this algebra, which is nice, it's type 2, but how can we construct a trace on this algebra? And for this, we will mainly use modular theory. So the usual trace just doesn't work because there's too large a set of non-trace class operators, meaning that the trace would just diverge on those operators. So instead we use modular theory, and the main idea is if we can find some state, which we can call a tracial state, which is cyclic and separating, and has the identity as a modular Hamiltonian, then we propose this form for the trace. Namely, the trace will just be the expectation value in this tracial state. And it's already, if you know a bit about the modular Hamiltonian, we've already had lectures by Faulkner and some introduction by Source, then you already know that this will immediately imply that this trace is cyclic. Namely, because of this property here, because it would just be the identity. I've also written down the other properties of this modular Hamiltonian, but I will not go deeper into it since we've already had talks on this. So then what's our tracial state for this algebra? We will split it in 3 parts. So we have our usual state on the system, which is just the vacuum, could be the Bunch-Davis vacuum state for the sitter, for example, and it's our cyclic separating state with respect to which HS was defined from the beginning. Then for our clock, we take this special state, which turns out to be cyclic separating for the clock, and it's also the same states as considered in CLPW. And then for the rest of the clocks we consider, it's a bit special, because if you just consider those operators acting on a single clock Hilbert space, it turns out that there is no cyclic separating state for those. So that's why we have to take a second copy, and we have to create thermofield double states for those clocks. So we have to double these clock Hilbert spaces to get to these thermofield double states. And then one can prove that for this tracial state, we get just some projector for the modular Hamiltonian, so then we get what we want, because this modular Hamiltonian will act as an identity on this projected Hilbert space. So then we just set the trace as the expectation value in this state, and then we add some, for rescaling purposes, we add this exponential of s, which is just some constant, because this trace is defined up to some arbitrary scaling. And from this definition, we can get the trace on the physical algebra, namely just with this physical representation, and then we can immediately get, and then after some lengthy calculation, one can find the density matrix for an arbitrary state phi on an arbitrary physical state. And the only thing we have to calculate is this relative modular Hamiltonian. And then we immediately have our density matrix. And one can do the same for the reduced algebra, namely you just conjugate with this page-Rudis reduction map, and this gives us the density matrix with respect to the clock I. So the only thing you need to find the density matrix is just a relative modular Hamiltonian between our state of interest and our tracial state. Now, as far as the type of the algebra goes, we already commented that you need at least one clock, which you do not consider in your algebra, for it to be properly von Neumann. But the type, even if the algebra is of type 2, there's also a classification between type 2 and type 2 infinity. And that's given by looking at the trace of the identity. Namely, if we only consider one clock in our algebra of interest, then if we consider more than one clock in our algebra of interest, then the type of the algebra will be 2 infinity, mainly because we have this inner product of the thermofield double states, and those are not normalizable. They will lead to infinities. But if you only consider one clock, then you get the same case as in CLPW, namely you get a type 2-1 algebra if the spectrum of that clock is bounded from below. And that's also what they considered in the end of CLPW by projecting on the positive real line. So then, to compute entropies is very non-trivial because we have this the density matrix looks very non-trivial, and you have different operators which do not commute with each other. So you have to make use of the PCH formula. But there is a regime which CLPW also considers, and which we call a semi-classical regime, where it's fairly easy to calculate entropy. Namely, we assume that our physical state is peaked around some particular orientation of our clock, and we also assume that the QFT degrees of freedom of our physical state, that they're approximately stationary. So they approximately don't evolve in this time window, and it's the same as if our quantum clock actually acts as like a classical clock for the remaining degrees of freedom. And in this regime, you can prove this formula here, which is exactly, looks very reminiscent of the formula in CLPW and also in the generalization by Jensen, Soares, and Speranza. Namely, we have the Hamiltonian of the clocks, we have the relative entropy between our QFT states, so between the tracial state for the QFT and our chosen state for the QFT. And then we have this observer kind of entropy here, which if you only had one clock, this would reduce to this integral of the log of the wave function, if you have read that paper. But this is basically what we call the frame entropy, because you can have multiple clocks, so they can also lead to an entropy contribution to the full entropy of our physical state. So it's kind of like a generalization of the generalized entropy they consider in the CLPW and Jensen et al. Papers. So these are the clock contributions, because our algebra also has some clock factors on it, which you take into account. So they can also add to this clock entropy. So if you only had one clock, it was just like this one observer. It was this integral of absolute value of the wave function times the logarithm of the wave function in the original paper by CLPW. By Gandasikar, Longo, Pennington, and Witten. But if you have multiple clocks, there will be multiple terms like this, depending on the wave functions for those clocks. All right, so then lastly, let's talk about something that's more interesting about quantum reference frames, namely the title of the paper, what I call the notion of observer dependence. For that, we go a bit back to quantum reference frames in general, because now if we have multiple clocks, then one can ask the natural question, okay, I can describe everything, our system, with respect to clock 1, but what if I instead describe our system with respect to clock 2? What's the change? So that just amounts to a change of description or a change of gauge. So if we just have two clocks, then we can, for example, we can dress everything with respect to clock 1, or we can dress everything with respect to clock 2. What's the difference then in these two algebras? So how this works is that we have our physical, so for the reduced algebras, it's the same. We have this physical Hilbert space here. Now these two algebras are isomorphic to each other, but you can both reduce them in different ways. So you can reduce them with respect to clock 1, you can reduce them with respect to clock 2. And then there's also a mapping between the two, which we call this V-map here. And this is kind of reminiscent of a manifold structure and changing coordinates on a manifold. Because you can regard your physical Hilbert space as like your manifold, your higher physical theory, which like has no coordinates, but contains all the physics you want. And by introducing this Page-Wooter's conditioning, it's like as if you're adding coordinates on that manifold, because then everything will be described in function of the time observable of clock 1. So that's why we call the physical Hilbert space in this sense perspective neutral, because you don't really pick out a perspective, it contains all perspectives at once. And then this VMAP, which is basically goes back to the physical Hilbert space and then to the other Hilbert space, we see as like a quantum coordinate change, just like how you would change coordinates on a manifold. But then how do these two differ in description of the system? I guess something went wrong here, but I'm not sure what should be pictured there. I'm not sure what went wrong with the presentation. Because I could just draw it. So what happens is, if you call this square the full gauge invariant algebra, so basically this property here, then for observer, we can look at the subalgebra, which is just the system with respect to clock 1 and the system with respect to clock 2. So it's like the system with respect to observer 1 and the system with respect to observer 2. So the total gauge invariant algebra of the system with respect to clock 1 would be like some subalgebra denoted by this horizontal strip, and the one with respect to clock 2 would be this vertical strip. And they do not necessarily have to overlap, because it's obvious that if the spectrum of the two clocks are different, then you can see this as kind of like different coarse graining of the system degrees of freedom. So these two algebras do not need to overlap at all. However, there are elements which are invariant which are equal for both observers, namely those elements that lie in the overlap on the blackboard, namely the small square, and those are exactly the elements which were already gauge invariant from the beginning. So they were the elements that are internal to the system and are gauge invariant under just the system Hamiltonian. However, we know that if our system algebra is of type 3, then those elements are just the identity, it's just complex scalars, so it's kind of a trivial algebra. But since we have the different observers with different clocks, with different properties, they decompose the total gauge invariant algebra in different ways, we get that notions that depend on the definition of subsystem, like temperature, or in our case entropy, will in general depend on the quantum reference frame you choose to describe the system. And this we give as a reason to conclude that the gravitational entropy for such an observer is also observer dependent. Namely, let us look at some physical states that describes everything in the patch in our subregion of interest. So on the gauge invariant level, we have some physical states, and then we have two observers, so we can reduce to the left, we can reduce to the right. We have a state with respect to observer 1, we have a state with respect to observer 2, and those are connected by a unitary, namely by this VMAP. So every state here in this triangle contains the exact same information. However, if you look at the algebra side of things, we have the total gauge invariant algebra, but it's logical to assume that observer 1 does not have access to, for example, operations on the second observer's clock, and observer 2 does not have access to operations on the first observer's clock. So then observer 1 would only have access to a subalgebra of the full gauge invariant algebra. So they would only have access to one of these two strips. So we can reduce this to the page-rooters level to say that, we just have the system algebra with respect to observer 1. On the left, we have the system algebra with respect to observer 2 on the right. But these two algebras are not unitarily related to each other through the same VMAP as the states were related. And this already kind of tells you that the entropy will be different, because the entropy is always defined with respect to some algebra. And here we already established that these two algebras with respect to different observers will not be unitarily equivalent. So that already implies that indeed they will measure different entropy from their perspective. And there are different reasons for this. For example, the clock spectra they use can be different. You can have a degenerate versus non-degenerate clock. You can have one that's periodic or periodic or monotonic, or there could be a different entanglement structure between the two states on this level and on the level of the respect to clock 2. So as an example, let us make a very constructed example. So let's say we start from the state with respect to observer 1, we assume that it's some projected product state where the wave function of clock 2 is in some superposition of 2 clock times. So you can imagine that you have some branch, some vertical branch. You split the branch with some beam splitter or something. I don't know. I don't do experimental physics. But you send one branch to a massive object. The other branch just stays on its course. And then you combine the branches again. Then there will be some time shift between these two branches. And this will lead to a superposition state for clock 2. And for clock 3, we just say it's just some clock state with a clock spectrum that's nearly ideal. It's not that important. But then what happens if you apply this VMAP to look at the clock, to look at the state from the second observer's perspective, this superposition here will turn into entanglement for the second clock. So it already tells you that superposition, so here it's a product state for observer 1, for observer 2 it's an entanglement. It's an entangled state, so you would already say that, okay, yeah, the entropies will be different. And it also turns out if you do the calculations, then we have the two density matrices for both observers. And you can already see here that, for example, in this one, the wave function of clock 2 doesn't play a role, but here it will play an important role. So if we make some assumptions, and we just look at the QFT part, so we kind of like ignore these exponentials here in front and only look at these parts of the density matrix, then the entropy part, the QFT part for observer 1 is fairly straightforward, just a log of the modular Hamiltonian conjugated by these projectors that make sure that the constraint is satisfied. But because of these wave functions here, for observer 2, it will look much different. Namely, you have these two terms, one where you have evaluation at minus ∆2, and the other where you have kind of this modular Hamiltonian with the QFT state at minus ∆2 minus delta tau. So you have like two contributions. And so in this case, you can consider two sources of observer dependence. Namely, you have a different entanglement structure. Namely, this term here can be recast in the form as a commutator between the modular Hamiltonian and just the log of this projected modular Hamiltonian, modular operator. And the second source of observer dependence is namely if sigma 1 is different from sigma 2, namely the clock spectra are different, so the fuzziness is different, then this kind of like coarse graining of the modular operator, of this delta, the modular operator will also be different. So this specifically this log pi 1 delta pi 1 piece will be different for both observers. So even if you take delta tau to 0, but the clocks are different, then you would still find that the entropy between the two observers will be a different numerical value. And that's really like an explicit example of what we call the observer dependence of gravitational entropy, since these two contributions contribute to the total entropy of the state. So then I now come to the end of the talk, and I'll leave it at this slide with the main takeaways from our paper and from this talk, and I'll be here to answer any questions. Yeah? Well, the derivation you're referring to is kind of hidden in this third term. Namely, if you would use like some Kahn's co-cycle theory stuff, and you would write this as the relative entropy of psi s double bar phi s instead, you would get this extra like expectation value of hs, which then would be your log area, which would be like your area term. Mm-hmm. Observer dependence. How does this show up in terms of what does this mean? If I use different clock cells, delta. Yeah, that's something we kind of still working on in a follow-up paper what exactly this means for like the area term. Because of this projectors in the end, we have like kind of this coarse graining of the modern Hamiltonian. So normally if the clock was ideal, you would not have these pi's, and this log would like exactly be the definition of your relative entropy, right? Yeah, indeed. And in the follow-up paper, we actually look at this case where we show that linear corrections, they show up at beyond this gravitational piece. So both observers would indeed agree on this area term, but there would be this extra term, like for example, from the entropy of the clocks, that would be different between two observers. But since that's part of the total entropy they measure, that's why we call it the total observer dependence of the entropy.
Is this observer-dependent entropy has some maximum, or it can be arbitrarily large?
Do you mean like the difference between the entropies or the entropy itself?
I guess the entropy itself is divergent, so
that depends again. If you're depending on how many clocks you take into account, your algebra will either be type 2-1 or type 2 infinity. And the differences are really whether there's like a maximal entropy state or not. Like if you're in type 2-1 case, then yeah, there would be some bound on like what the entropy itself can be. But if you're like in a type 2 infinity case, so if you have multiple clocks in your algebra, then there is no bound in the entropy essentially.
I see. And even if you consider some the difference of entropy with respect to some reference state, the entropy can be infinitely large.
That I'm not entirely sure of whether that difference can be infinitely large. I cannot answer for the moment.
I see. And could you remind me what was the definition of this pi conditional 1 or pi conditional 2?
This one?
Yeah.
So this projects on the overlap between your system spectrum and minus the spectrum of the clock, because then you know that there will always be eigenvalues such that the full constraint is 0.
Okay, thank you.
Thank you very much. And